Hello everybody, let's have our video about how sharp can telescopes make images. Remember that we want to make telescopes as large as possible for two different purposes. One, to make objects brighter, that was the subject of our previous video. And then the second is to get as detailed as images as you can, as sharp of images as you possibly can. Something that astronomers refer to as good angular resolution. So what is angular resolution? Well, let's go ahead and get our slides up and start going through and see if we can make sense of this deceptively simple concept. Sounds confusing at first, but once you get a hang of it, it starts making sense. So we're going to be talking about angular resolution, and we're going to remember that we want to improve angular resolution, get better angular resolution, get more detailed images by making telescopes as large as possible. But let's start with a practical application of what angular resolution means and what angular resolution is. So here is an image of the sky. You maybe have already picked out that this is looking at the Big Dipper, which you can see right here. And we're going to ask a question of, let's take a look at the Big Dipper. So there I've highlighted the Big Dipper, so hopefully everybody can see that now. And then let's look right there. Is that one star or is that two stars? And I encourage you to go outside. You can see the Big Dipper from Knoxville. You can see the handle of the Big Dipper and all the stars that are there. Go out and take a look tonight or sometime soon, whenever it's clear outside, and look for this star in the middle of the handle of the Big Dipper. And ask yourself, is that one star or two stars? This has been used as a vision test throughout history before we had pesky things that looked like this. In fact, it was one of the vision tests that supposedly was given to soldiers in the Roman army. Okay, so the question is that one star or two stars? Is there just one star there, or are there two stars so close together they get blurred together and you can only see it as one point of light? Depending on how good your vision is, you might see that there are indeed two stars there. I can zoom in a little bit, and now on the screen, it becomes pretty clear that those are two different stars. They are separated by a small angular separation, about 12 arc minutes, but those are starting to become clearly two stars instead of one star. When you go outside and look with the naked eye instead of on a screen like this, you may not notice that they are, in fact, two stars. You might only see one star, and that's perfectly fine. It's most uh, people that have 20/20 vision can see there are two stars. I'd say by the time you're getting to like 20/60 vision, they're going to start blurring together or so. So if we really zoom in, which I've done here, definitely two stars there. We have Mizar, the brighter one, and Alcor, the dimmer one. So here are Mizar and Alcor, and they have an angular separation of 12 arc minute. People with decent vision, you can walk outside, test yourself as soon as you can, go enjoy the Big Dipper. You're just going to be in the northern parts of the sky. But go ahead and take a look and see if you can see these as two distinct stars or not. They have an angular separation of a 12 arc minutes. So people with decent vision, and it'll work if you have decent vision with glasses or contacts. It'll work with decent vision if you don't. And see if you can see those as two distinct stars. Why is it that some people see them blurred together and other people see them as distinct points? The ability to actually distinguish these two stars as distinct points, that's what we're talking about when we're discussing the topic of angular resolution. If you can see both stars, we would say that the stars are resolved. The angular resolution of whatever you're viewing it with is good enough to see them as two distinct points of light. However, if they're blurred together into a single blob, then they are unresolved. And whatever you're looking at, maybe it's your eye, whatever you're looking at the stars at, it does not have good enough angular resolution to see that those are two stars instead of uh, uh, it can't see that they are two stars. Instead, it sees that as blurred together as one single blob. And that's what we're talking about with angular resolution. So let's actually get into the definitions of it. And this is really coming down to, again, another example of why is the Milky Way milky looking? So here we can see the Milky Way, and this portion right here looks just like a white blur. However, if you're going to take Hubble, a telescope that has fantastic angular resolution, and we're going to look at this blur of white, the milky part of the Milky Way, and zoom in, you'd notice that, oh, it's not just a milky blur. It's made up of a bunch of stars that are just crammed really close to one another. In fact, they're so close to one another that the human eye can't see them as distinct points of light. They are unresolved. So they all get blurred together into this milky blob in the sky that we call the Milky Way. Galileo was actually took his telescope and pointed it at the milky part of the Milky Way, the Milky Blur, and was able to determine the same thing. So you can see this with a small pair of binoculars or a small telescope, that the Milky Way part of the Milky Way is really just a bunch of stars that are so close together that the human eye can't resolve them into stars, separate stars. It can't see them as distinct points of light. It blurs them all together into a blurry blob. So we are going to describe this using the term angular resolution. You are familiar with the term resolution because we all have computer screens and TVs and things like that. So whenever we say resolution, we're not really talking about anything different. We're talking about the finest points of detail that whatever you're talking about can make. Better resolution means more detail. But we're talking about angular resolution because remember, we can't tell the physical separation, like what is the distance between these points. We can only tell how far apart they are. What is their angular separation, measured in something like arc seconds or arc minutes. So the angular resolution of an optic, which is just something that sees, so your eye, a camera, a telescope, those are all examples of something that sees. So the angular resolution of a telescope, the angular resolution of your eye, is really describing your ability or its ability to distinguish two adjacent points, 2 points really close to one another, as individual points instead of them being blurred together into a single blob. Do you see a milky blur, or do you see all the points of light that are individual stars? Do you see a single star in the handle of the Big Dipper, or can you resolve and see Mizar and Alcor as two separate distinct objects? And specifically, the way that we're going to refer to this, since we can describe, say, this red star and this red star, let's say that they have an angular separation of 10 arc seconds or something like that. We know the angular separation between things. So the way that we're going to talk about this, and I'm going to spend a lot of time in this video trying to give you a way to reason this out and to understand it. But if two objects are separated by less than your eye's angular resolution or less than your telescope's angular resolution, whatever that value is, then the objects get blurred together into a single blob. If, however, the angular separation is more than the angular resolution of your eye or the angular resolution of the telescope, then your eye or the telescope can see those as two distinct points of light, and we say that things are resolved. So what we're going to be doing is we're going to be comparing the angular resolution measured in arc seconds or arc minutes of a telescope to the angular separation of objects in the sky. And if the angular resolution of your telescope is smaller than the angular separation, then you can actually see those objects as distinct points. You can resolve those objects. You can see the detail. So we're comparing the angular resolution of a telescope to the angular separation of things in the sky. And we want the angular resolution of the telescope to be smaller. It's saying that's the minimum distance two things can have, and you can still see them as distinct points. So we really want the angular resolution, whenever we talk about the numerical value of it, the angular resolution and say number of arc seconds, we really want that to be a super duper duper small value. Because the smaller the value, the better the angular resolution. So whenever you hear me say better angular resolution, I'm talking about a numerical value is smaller because that's telling me how small of an angular separation I can still preserve detail at. Okay, now that we have a little bit of priming there, let's look at this practically. Because I've been saying a lot of terms that hopefully you're a little bit more familiar with, but maybe you aren't fully incorporating all those ideas so you can just hear the vocab and connect the ideas instantaneously. So let's take a look. Here we got some creepy looking eyes. And here we have two stars. And we would describe how far away the stars are apart from one another in the sky using angular separation. So these stars would have an angular separation. The human eye, as something that sees, is going to have an angular resolution. For good vision in the human eye, like 20/20 vision in the human eye is about half to 1 arc minute angular resolution, which means, so let's just say 1 arc minute because it's easier to say that. Let's say that my eye has a angular resolution of 1 arc minute. So if I'm looking at these stars and the angle between them, their angular separation is larger than 1 arc minute, so this angle is bigger than the angular resolution of my eye, I can be like, hey, I see Mizar and Alcor. I see you as two distinct stars. However, if this angular separation is smaller than the angular resolution of my eye, so this angular separation is smaller than 1 arc minute, say a tenth of an arc minute, then my eyes cannot distinguish these as distinct points of light, and these two stars get blurred together into a single blob of light in the sky. Let's do another practical example, and for this, you will have to pause the video, but wait for me to go ahead and say pause. I wanted to first describe what you're seeing here. This works great in a classroom, and I was really struggling to figure out how to translate this to a video, but I think this works pretty well. So what I've done here is I've just made a series of dots. There is a certain amount of white space between the dots. There is an angular separation between them. And with each row, that angular separation gets smaller and smaller and smaller and smaller. So this angle with each row gets smaller and smaller and smaller and smaller. Even with me being as close as I am to my screen right now, this bottom row right here looks like a line. But trust me, it is a series of dots. I can go ahead and show you that if I go ahead and I zoom in. So you can see that that bottom row is indeed a series of dots. This is a series of dots. This is a series of dots. The white space is just really, really small. So there's a small amount of angular separation between them. So as you move further and further and further away, the angular separation will get smaller and smaller and smaller and smaller. So what I'd like for you to do is pause the video so you're stuck on this screen right here, and then move away from your computer screen, and you'll start to see from bottom to top, the rows of dots will start to look like lines. It's only going to work for the bottommost ones, but when that happens, so I'll assume that you've paused. And now that you're back, so as you were moving away from the computer and you started to see this row of dots turn into what looks like a line, what was happening is you had moved far enough away so that the angular separation, the white space between those dots, was smaller than the 1 arc minute angular resolution of your eye. So your eye could no longer see those as a distinct dot, so it blurred them together. And since they're all nice and lined up in a row, they blurred together into what looked like a nice straight line. And possibly it even worked for this one. I doubt it worked for the higher ones, but I wanted to give you a practical example of angular resolution so you have something intuitive that you can think back on. Now let's talk about how this actually works. Let's talk about the nature of angular resolution and what gives rise to the nature of angular resolution. So we are going to be talking about the equation of angular resolution. We'll start with the proportionalities. So remember, the proportionalities tell us what a physical phenomenon, here angular resolution, depends on. So it relates the different variables involved. So the angular resolution of your eye or a telescope is going to be directly proportional to the wavelength of light. So this little fishy looking symbol is the proportional to symbol in mathematics. So the angular resolution is directly proportional to the wavelength. You go to longer wavelengths, the angular resolution value gets larger. And remember, larger is bad, which means that things will get blurrier for longer wavelengths. Your ability to see 2 points as 2 points goes down for longer wavelengths. So the angular resolution is directly proportional to the wavelength of light. And it's inversely proportional to the diameter, the size of your telescope. If you want to think of your eye as a telescope, the diameter of your pupil. So the angular resolution is directly proportional to wavelength. Shorter wavelengths, smaller angular resolution, the closer two things can be together, and you can still see them as distinct dots. Larger wavelength, bigger angular resolution, and things can be separated by a larger distance and they get blurred together. And it's inversely proportional to the diameter of the telescope. As I make the diameter of the telescope bigger, say from 1 meter telescope to a 2 meter telescope to a 5 meter telescope to an 8 meter telescope, as this number gets bigger, I'm dividing by a bigger number, the angular resolution gets smaller, which means that two things can be squeezed together closer, and I can still see them as distinct points. So we can make the angular resolution smaller by observing at shorter wavelengths or by building telescopes with larger diameters. And remember, building a telescope with a larger diameter is also going to make faint objects appear brighter. We get a double win here. And remember that smaller angular resolution means that 2 points can be very, very close to one another, a very, very small angular separation between them. And you can still see them as distinct points. Okay, so why is this? Why can't we just infinitely see detail? What controls and limits the detail of what our human eye can see and of what telescopes can see? We can't see things with infinite detail. There is a limit to it. What about the natural world causes that? And here we have to go to another wave property, a wave property called diffraction, which is a colloquial way we can call that is light can bend around corners. Waves bend around corners. So diffraction is a wave property that describes how a wave will spread out as a result of passing through a narrow opening. So these are actual images of ripples on water. And these black parts right here is just like blocking. You put down something into the water, which blocks a wave, this ripple on this side, it blocks it. And so you can watch how the wave will propagate as it goes through a narrow opening. Just like if you were to go to a harbor or a bay at the sea and it had a very narrow opening, and here come the ocean waves, they would hit the narrow opening. It's not like you just have this little tiny wave that is as wide as the opening was that goes straight to the shore. That wave spreads out through the entire bay. This is what we're looking at here. And here you can actually see the bright parts are the crests of the wave. So you can actually see the ripples with this image. So you can see that as the wave comes through, it hits this barrier, goes through a small opening, and you can see it spreads out. As that opening gets smaller, it gets a little bit more complicated, but it's still spreading out. And if you have a really, 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 really small opening, it's nice and controlled. And here comes our wave. All of our wave fronts, all of our wave crests are in a nice straight line. Hits this very narrow opening, and it spreads out radially. So you can see the wave as it spreads out and goes out into, say, the bay that we're talking about. So here we can actually see the effect of diffraction. The wave doesn't just hit this barrier and go straight through, it bends around the corners some. And that, what we're observing here is diffraction. It describes how a wave will spread out, and it depends on how big the opening is and the wavelength of light, or the wavelength of these waves. And we're not going to go into the details of diffraction, but due to this, this is going to give us a natural limit to our eye's angular resolution and to a telescope's angular resolution. Now, all has to do with the pattern that's being formed as a wave goes through this narrow opening. So light is a wave, and we can do the same thing with light. And I wish I had all the tools that I have in the classroom, because I bring something to actually show that you see this pattern. If you shine light through a very narrow opening, something that looks like this. So you shine light of a single wavelength through a very narrow opening, then that wave will spread out. Notice that this pattern looks just like this pattern up here. And if you were to look at how bright it is, so you were going to put a screen right here so you could see what the light looks like, you would actually see that you have a bright line in the center, and then symmetric around it, you have dimmer and dimmer lines. This is caused by this diffraction, this light, as it bends around the corners as it goes through the small opening. And yes, I guarantee you, you actually get this pattern. And this is what we call a diffraction pattern. So this is light passing through a vertical slit opening. If you pass light through a circular shaped opening, a circular shaped aperture as we'd call it, then you don't get a pattern that looks like this. You still get a bright central part, but then you get rings of dimmer and dimmer and dimmer. So you get a bright central part and then rings that get dimmer and dimmer and dimmer. So this is the diffraction pattern caused by passing light through a circular opening, like the shape of our pupil or the lens on a refracting telescope or the circular opening that leads to the primary mirror in a reflecting telescope. So anytime we're observing something with our eye or with a telescope, we're going to get a diffraction pattern that looks like this. So how does this actually limit what we can see? Let's break this down to a simpler view. So let's imagine we have this true point of light, a single point of light. So a star that's so far away that you can't really measure its angular size. So here we have a point of light. And what we're going to do is we're going to let that light pass through a circular opening. Maybe that's the pupil. Maybe that's a telescope. And I made this one look like a telescope. And as that light passes through the circular opening, what you're going to end up seeing, because light passed through a circular opening and diffraction is going to happen, you don't see a single point of light. What you see is this diffraction pattern. For the curious, this diffraction pattern is called an airy disk, A-I-R-Y. But this is what you see. And really, you can most easily see this central bright blur, and the angular size of the central bright blur caused by diffraction is the smallest image that a telescope can make due to diffraction. So we have a point of light, and just because of how diffraction works, a wave property of light, passing that light through a circular opening gives it, so we can't see a point of light, we see this blurry blob instead, which is going to be the smallest image a telescope can make. What determines how big of a blob this central region is and then where these rings are? The diameter of the opening and the wavelength of light. Almost as if we can relate the smallest image that we can see in angular resolution to the wavelength of light and the diameter of a telescope. So the smallest image that we can see, the smallest amount of the smallest detail we can see is proportional to the wavelength divided by the diameter, directly proportional to the wavelength, inversely proportional to the diameter. Why is this? Well, we just saw that is diffraction. Diffraction is giving us the smallest image we can form with a telescope or with our eye. So what do we call this smallest image that we can see? This smallest resolution that we can see using a telescope or our eye? We call that the diffraction limited resolution, because it's something that's being created by diffraction. That's what's causing the limit. So when we talk about telescopes, when we talk about the angular resolution of a telescope, we are talking about the diffraction limited angular resolution of a telescope. And this is the best possible resolution given the size of a telescope. It is the smallest image a telescope can make. And it depends on the wavelength of light you're observing at and the size of the telescope. make the size of the telescope larger, and the diffraction limited angular resolution measured in arc seconds or arc minutes gets smaller and smaller and smaller and smaller. You can see a smaller and smaller and smaller, well, you can form smaller and smaller and smaller images. You can preserve a lot more detail. So instead of always saying diffraction limited angular resolution, we usually just say angular resolution of a telescope. And it's really telling you the smallest image a telescope can make. If you can remember that point, then this becomes a little bit easier to handle. I want to show you that, yes, since this is an astronomy class, this is a science class, that yes, you can calculate the angular resolution. So if you're curious about the angular resolution of your eye, you can plug in the numbers, the diameter of your pupil, about 2 or 3 to 4 millimeters, the wavelength of light that we're observing at, measured in microns, about 0.5 for visible light, 0.55 for visible light, and then just multiplied by some number. And that'll give you your angular resolution in arc seconds. You do not have to calculate angular resolutions in this class, but I wanted to show you, instead of having the proportional to, we can always replace proportional to with an equal sign if we use a little bit of extra knowledge. So the angular resolution equals 0.25 times the wavelength of light you're observing at divided by the diameter of the telescope. Let's do a practical application of this, something that you might want to know for upcoming quizzes and exams. So let's take a real telescope that's going to be launching hopefully soon, the James Webb Space Telescope, the spiritual successor to the Hubble Space Telescope, is going to be launched into outer space, and it has a diameter of 6.5 meters. It operates primarily in the infrared, centered on about 1 micron wavelength, 1,000 nanometers, just a little bit redder than red. So what would the angular resolution of the James Webb Space Telescope be, operating at 1 micron wavelengths? I can use that equation, 0.25 times the wavelength, 1 in microns, 1 micron, divided by the diameter measured in meters, 6.5, calculate that away, and I get the angular resolution of the James Webb Space Telescope is 0.0385 arc seconds. That's the smallest image that the James Webb Space Telescope will be able to make. It's the smallest amount of detail it can see. So let's imagine what would happen if we take James Webb Space Telescope and we point it at the second closest star to the Earth, Alpha Centauri. It's 4.37 light years away. It's about the same size as the sun. So using that same thing of angular size and distance that we covered it before, I went ahead and calculated out what would its angular size be in the sky if we could see an infinite amount of detail. The star would have an angular size from one side measured to the other side of 0.0067 arc seconds. That's the true angular size of Alpha Centauri in the sky. What would James Webb Space Telescope see? Well, James Webb Space Telescope, the smallest image it can make, is much bigger than 0.067 arc seconds. It's 0.0385 arc seconds. So even though that's what Alpha Centauri's true angular size is, what James Webb Space Telescope wouldn't see, it wouldn't see just the star, it would see a blurry blob that has a size of 0.0385 arc seconds. Because that's the smallest image that the James Webb Space Telescope can make. So we see a blurry 0.385 arc second image of the star, even with this giant space telescope. Has not launched yet. Hopefully it'll be launching soon. Okay, let's do another practical example. Let's take the Hubble Space Telescope and play the same game that we kind of played at the beginning of this video that we played with Mizar and Alcor. So the Hubble Space Telescope has an angular resolution operating at in the visible part of the spectrum. Let's go to the center of the visible part of the spectrum, 550 nanometers, 0.55 microns, 0.55. And at the size of Hubble, it's a 2.4 meter telescope. Notice the James Webb is quite a bit larger. So what is the angular resolution of Hubble operating in the visible part of the spectrum? 0.25 times 0.55 divided by 2.4, 0.06 arc seconds. So the smallest image that Hubble can make is 0.06 arc seconds. And this symbol right here means arc seconds. So what I'm going to do is I'm going to represent that angular size, the angular resolution of Hubble, the smallest image it can make, by just a line that has a certain length to it. And what we're going to do is we're going to play a game where we're going to look at stars that are separated, have an angular separation of some amount measured in arc seconds, and consider what Hubble would see in that scenario. So here we have two stars that have an angular separation, so they're really, really close to one another in the sky, of 0.02 arc seconds. Notice that angular separation, that distance is smaller than the angular resolution of Hubble. It's smaller than the smallest image that Hubble can make. So Hubble cannot make two separate images of stars. They all get blurred together into a single blob that would have a size of 0.06 arc seconds. So in this case, Hubble can't see that these are two separate stars. It sees both stars blurred together into a single blob. At 0.04 arc seconds, sure, they're separated by more, but that angular separation is still smaller than the smallest image that Hubble can make. It's diffraction limited angular resolution. So both stars, again, get blurred into a single blob. Now, if you had two stars that are separated by 0.08 arc seconds, this angular separation is larger than the smallest image that Hubble can make. So Hubble can make an image of this star and a separate image of this star, and it can see both stars. The angular separation is larger than the angular resolution of Hubble. Hopefully that helped you understand angular resolution, put a little bit of context to what I have in the textbook slides. If you have any questions, be sure to post them in the week 8 discussion. This is one of the more important concepts of this part 5 of unit 1. And I really want to make sure everybody gets it. And that's why I spent so much time with this video. All right, thanks everybody.